Hello everyone! Today we are going to dive into a highly practical and dynamic concept in structural engineering, influence lines for determinate beams. Up until now, we have mostly dealt with static, stationary loads. We know how to draw shear force diagrams, SFD, and bending moment diagrams, BMD, when the load stays put. But in the real world, think of bridges, highway overpasses, or crane gantry girders. Loads move. How do the shear and moment at a specific point change as a vehicle rolls across a span? That is exactly what influence lines will show us. Let's get started. Let's look at a simply supported beam, AB, of total span L. We want to monitor a fixed section located at a distance x from the left support. Imagine a unit load of 1 rolling across the beam. For the shear force ILD, when the load is to the left of our section, the ordinate is -A/L. Just to the right of the section, it jumps to a positive peak of Lx divided by L. To the left, the peak is -x divided by L. For the bending moment ILD, the diagram is a triangle peaking directly under the section. The maximum peak ordinate is calculated as x multiplied by Lx/L. We will use these standard shapes to solve our numerical problem. Let's apply this to a practical problem. Please write this down. A single rolling load of 100 kilonewtons moves on a girder of span 20 meters. We have 3 clear objectives here. 1. First, construct the influence lines for shear force and bending moment at a specific section located 5 meters from the left support. Let's call this section point D. 2. Second, construct the influence lines to find the points where the absolute maximum shear and moment will develop across the entire beam. 3. Third, calculate those absolute maximum values. Let's calculate the values for our section first. Let's focus on section D, where distance x is 5 meters and the total span L is 20 meters, leaving 15 meters to support B. Let's calculate our peak unit ordinates. For the shear force ILD, the positive peak just to the right of D is Lx divided D is Lx divided by L, which equals 0.75. The negative peak just to the left is x divided by L, which equals 0.25. For the bending moment ILD, the peak directly under D is x times L, x divided by L, which gives us 3.75. To find the actual maximum forces caused by our 100 kilonewtons rolling load, we multiply the load magnitude by these peak ordinates. Max positive shear at D, 100 kilonewtons multiplied by 0.75, equals 75 kilonewtons. Max negative shear at D, 100 kilonewtons multiplied by 0.25, equals 25 kilonewtons. Max bending moment at D, 100 kilonewtons multiplied by 3.75, equals 375 kilonewtons. Let's look at the absolute maximums for the whole beam. To finish up, let's find the absolute maximum values anywhere on the beam. Absolute max positive shear. This occurs at support A, where the ordinate is 1. 100 kilonewtons times 1 equals 100 kilonewtons. Absolute max negative shear. This occurs at support B, where the ordinate is -1. 100 kilonewtons asterisk -1 equals -100 kilonewtons. Absolute max bending moment. For a simply supported beam, this always happens at the midspan, where x equals 10 meters. The peak midspan ordinate formula is x times Lx divided by L, which is 10 asterisk 10/20, equaling 5. Multiplying by our load, 100 kilonewtons times 5 equals 500 kilonewton. Notice that 500 kilonewton is much higher than the 375 kilonewton we found at section D.